So, good morning, dear participants. It gives immense pleasure to welcome all of you to the third day, first session of the workshop. So, today, the first talk will be delivered by Professor R. Panneer Selvam. He is a university professor working at the Department of Civil Engineering, University of Arkansas, USA. Professor Panneer Selvam, he is basically from India. He moved about 40 years ago to USA, and he has a vast knowledge in mathematical modeling. He has written a book to deal with the finite element method, and he has done a lot of projects. The research projects done by him was relatively useful in many aspects, and he also deal with many consultancy projects, and he also give consultants to the engineers who need some mathematical modeling and civil engineering support. In finite element method, Professor Panneer Selvam has contributed significantly. That was well recognized by his strong publications in reputed journals. Today, Professor Panneer Selvam is going to deliver a talk on finite element method to study fluid flow and heat transfer in trapezoidal cavity. Professor Panneer Selvam has vast knowledge on the generating the elements for complex domains and simulating the characteristics of the fluid flow and heat transfer characteristics on various aspects. Professor Panneer Selvam has written different codes and used various softwares, and today he is going to use the software ParaView. And by chance, if anyone is interested to use ParaView, it is an open source software. Maybe after the lecture, Professor Panneer Selvam will give you some, during his lecture, whatever the small data he used, that we can share with you. You can also simulate the results and understand and further things. And Professor Panneer Selvam has about 40 years of knowledge in this particular field. So with this small introduction, we feel happy and honored to have your lecture in this workshop. And over to you, sir.
Thank you. Everybody can hear me well?
Yes, sir. Slide is visible and your audio, video, everything is perfectly all right, sir.
Okay, good. I think I gave the topic. This is what Professor Sivaraj asked for it, but I kind of modified few things. But anyway, on the way I will explain it. And let's go one by one. I'd like to thank Dr. Sivaraj for giving me this opportunity to give this talk. I also like to acknowledge current support I have from National Science Foundation, which is through Iowa State University, which is a very large project. And as he said, I am from Tiruvannamalai in India. I have been living in Fayetteville for 39 years and in the US for 44 years. And my place is right in the northwest corner of Arkansas. With that introduction, I also like to request you all, since it's a workshop, I intend to cover several topics. Please ask questions when I'm discussing the particular material itself. I remember maybe yesterday, because of some noise, everybody was silenced. If that is so, I'm sure if you can send the text to the group text or whatever the text, Professor Sivaraj can be able to read and tell me the question, then I can respond also. With that, I will, as I said, he provided this topic and listed in the program. I intend to discuss some on that. I also want to give some introduction from the finite difference method point of view, because most of you are familiar with finite difference method. So I thought through that, when you look at it, maybe finite element method, you may be able to see them much better. Before that, I also felt because finite element evolved from structural engineering group, from civil engineering. So we have an extensive from the undergraduate different courses itself, kind of indirectly we were taught finite element, not knowing finite element actually, to be very frank. Then you take regular courses, so there's a very deep understanding is there. So I strongly suggest for anyone to understand very well, take a course, finite element course in engineering. This helps a lot in basic understanding. With that, I also thought put few books. This is a book, introductory book on the left side by Professor Chandra Uppala and Belugundu. And that's a very good book. I actually even use it for my graduate level finite element class. Then this is a book for fluid flow, which is, I consider, very little bit deeper finite element form. And then these are classical books, finite element procedures by Bede, and also finite element method by Zinkiewicz, volume 3. These are also much more deeper ones, but very good. So I thought it's good to expose you guys with some of the books in case you want to know more about it. And also some of the materials here, I also use this, my book, for my class when I teach CFD. So there are several aspects of it. I take it also for discussion here. And just to make it more clear, I would be discussing mostly in this workshop incompressible flow problems. I will not be discussing anything compressible flow, multi-phase flow, turbulent flow, and modeling. If you look the last 5 or 7 years, I'm deeply involved in understanding the fundamentals of turbulence and turbulent flows and peak pressures and how to develop inflow turbulence and all, but not in this lecture. I'm going to talk anything. Mostly I'm focusing on incompressible flow, finite element modeling, even moving grids, adaptive finite elements, geometry conservation law. There are a lot of interesting things with respect to fluid mechanics. It is there, but I'm not discussing them. So main topics planning to discuss: introduction to finite element for CFD, convective heat transfer in a trapezoidal cavity, hands-on paraview visualization for finite element methods, triangular grid. I have requested Professor Sivaraj to convey everybody to download paraview, and also I sent a data file fmet.vtk. I hope you all have that. Then you could also, when I'm doing it, you could also do the same thing in your computer. That way you can also learn. And we will, I don't know the status because I requested him, but there were communication issues, so I'm not clear. But anyway, I hope you can also look into that. But if not in the there are certain things arranged, since they are putting the presentation in YouTube or whatever. There are certain simple data also, I'm showing it in the presentation, but the finite element data for flow, what do you call it, stress concentration problem data, it's a little bit more sophisticated, a little bit more involved, more data points, I think. But anyway, if you can able to get it, see whether you can also do it with me. And I will try to take that problem and try to show that at the end. As I said, this is a incompressible flow equations, and I think the diffusion part of it is very similar to finite difference method. It's very, I mean, generally it's a much linear form of things, so much easier to model it. But it is a convection term here, it is very sophisticated, and the continuity and the momentum connection, or the pressure velocity coupling, how it is implemented is a challenge. Anyway, we will discuss whatever we could and see where we go from here. Methods used: finite difference, finite element methods, control volume methods. And I think I would say it's a control volume method is between finite difference method and finite element method. This allows us to apply for unstructured grid easily. I use finite difference, control volume, finite elements depending upon the nature of the problem in the last 45 years. I was introduced, I told you, formally finite element. I took a course, I think 1981. From there, several different courses I took, and then I spent a lot of time in developing lots of different codes for finite element. Anyway, so I think the more you spend time and understanding the basics, it is possible. Generally, finite element method takes more memory and computer time, but FEM is more accurate than finite difference method for the given space, especially for CFD problems also. Major contrast: finite difference method, for incompressible flow, initially staggered grid is used. Then they have developed non-staggered grids. I will give what is that. I will explain it to you also soon. What is staggered and non-staggered? Mostly structured grids in the past. I will also explain what is unstructured. Now unstructured grid can be used. The major important one is you approximate the partial differential equation with proper boundary condition. Whereas finite element method, elements that are used, because in the last 2 days you have been listening to different talks, so I'm sure you are very familiar now what is finite element. Here, equal and unequal order finite elements are used for fluid mechanics or incompressible flow. Started with unstructured grid. Approximate instead of working with partial differential equation, you work with integral differential equation. Need to know variational principles. Boundary conditions are implemented elegantly comparing to finite difference method. So these are the major contrast. And just to give you some of these things illustrated, what do you mean, what I'm talking about? On the left side, if you can able to explain, able to refer the variable, say uij, in this case it's a 2D problem. So as a 2D array, as I shown with the ijk system, or 3D means ijk systems, not only the grid has to be orthogonal, it has to be, even it can be non-orthogonal grid, as long as you can represent them by this uij, that is called structured grid. If you can have any form of, not, it can be orthogonal, non-orthogonal, but the major thing is it is so complicated way that it can be the geometry. You only represent them by a single array with node numbers for each nodes and element nodal connectivity data you need. That is an extra data you need for finite element method of doing it in the traditional way of looking at it. And I think that is the major difference, I would say. And now, even in the recent years, control volume methods also started to come up this way. But as I said, the traditional ones I'm talking about. So unstructured grid needs element nodal connectivity data, which is the one, I'd say, major difference. Grid generation if the geometry is very complex, grid generation is a complex and time-consuming process. In many major projects, developing grid is a challenge, and people sometime in aeronautical and automobile and all, they talk about complex geometries. Even they may take months to develop the grid. So that's a major complications. Then coming to what do you mean by staggered grid? If the velocity, pressure, they are stored in different location, it is called staggered grid. And in the non-staggered means all the variables are stored in single place. And in the same way, in the finite element world, unequal order element. So one of them I try to show here. They call it Q2, Q1 element, which means is the velocities are stored on the dots, that means 9 points. The pressure is stored only at the corner points where the circle is. And it is a valid element. What do you mean by that? In these unequal order elements or in the finite difference world staggered grid, they supposedly satisfy a particular condition called Babuska-Bracey or Latishanka-Babuska-Bracey condition. So because of that, the solution for pressure equations converges very fast. And the overall, velocity pressure coupling is very good. If you use unequal order equal order finite element, that means is all the variables are stored at the same points, or in the case of finite difference non-staggered grid system, then the pressure velocity coupling is not as strong as a staggered grid system. But for arbitrary geometry, I think non-staggered grid is preferred, because staggered is no longer, it's very complicated to see. It may not be applicable also. But the finite element form, you could use the same, the Q2, Q1 element type, or any of the unequal order, you could use it. But the problem is, since all the U and V velocities to pressure locations are different, then the visualization, data manipulation are much complicated. So that's one of the reason many times these unequal order elements are not preferred, and we use most of the time, if we can, equal order elements. I have done both ways, and I think many problems, but I used equal order elements. Solution methods are the same for both procedures. Generally uses segregated solution methods. I know in the group, right, this group I'm talking, many of you through MATLAB and other places, they solve velocity and pressure together. But you can only do that for simple, smaller problems. But for larger problem, it is very difficult. Like, for example, I deal with 20 million nodes or 40 million nodes, like that, three-dimensional problems. It is very, very difficult to come up with a complete whole matrix to solve, because you are talking about these problems. I sometimes even have to run with even multiple processes put together many days. So in the common time places, people use this decoupling form, and that connection itself is a major discussion. There are a few I will discuss later. For equal order elements, special precautions has to be taken to circumvent the Babuska-Bracey condition, LBB condition. So anyway, those are the major highlights one should be looking. Then when you are assembling them, especially any unknown, because when you use segregated, what do you mean by segregated? Solving U, V, and P, each one of them separately, and then do a Newton type, you sub iterations overall to satisfy everything. If it is implicit, if it is explicit for convection, or momentum, then you only solve the pressure and go to the next time step. So in the finite difference method, for each equation, you can express them with 5 terms for 2D, 7 terms for 3D. Whereas in the finite element method, you have to use 9 terms for each variable in each equation, 27 terms in 3D. This is where the memory gets increased, and memory, not only memory, then the computer time also increase. But for the given same space, I would say that finite element is far more accurate. I will show some examples also with convection problem, then you will have much better understanding. And this is mainly to show that the flow has both diffusion and convection. But for high Reynolds number flows, convection is a dominant process. So we need to pay attention to that. This is a one-dimensional finite difference. I took it from a book for illustration. The one-dimensional problem to show that I am showing comparing with the exact solution for simple linear problem in the convection form. Finite difference in exact solution you could see from different methods. And the upwind commonly used is very highly diffusive. You can see comparing to exact solution what happens. Here I am trying to show 2 or 3 finite element method and maybe two finite difference method for comparison and 2 for finite element method for a same again linear problem of convection in a 2D space. Here you are looking at a cosine hill. I try to draw it as a contour varying from center 1 outside to be close to 0 or whatever, 0 is the cosine hill. So what the problem is, I try to rotate them 180 degrees. So since there is no diffusion in the problem, the one I took it, exactly it has to come back here. But you will see that the loss very much you can see. This is finite difference method with upwind. I put it down here. 88% are lost. Only 12% is transported here. The quick method is the workhorse in the finite difference world, and you could see that it can transport 44% for the same problem, for the same grid, whereas there's also negatively 4% or some numbers are there. It's a numerical dispersion. This is Taylor-Galerkin finite element method. I'm using it here. It transports about 70% of it, and you can see at least the shape somewhere close by. Then SUPG is another method in finite element world. People use them, but it has got a lot of diffusion. So it's very similar to finite element method, finite upwind method in finite difference. And it can similar to this, you can see that it only transports 22%. So one has to pay attention to convection modeling finite difference or finite element. And it is a challenge because there could be extensive error can come, and then you may not be able to predict the problem properly. The only solution is then you have to refine more and more. Then again, that takes a lot of computer time. Then coming to a Navier-Stokes solvers, coupled solver, where you solve, it's a nonlinear equation, but you solve them U, V, W simultaneously. That's what I put it in mathematically in a matrix form. X is the unknown, U, V, W, and P all together. I put in my world with large problems in engineering or science application, rarely used. But as I said, in your groups, I have seen people in the MATLAB using direct solution. But mostly commercial softwares, and in our research codes, every one of them, we will be using sequential solver, which is solve U separately, and then V, and then if it's a 3D, W, and then P separately. Then there's a way to connect them. That is what you call velocity pressure coupling. I will discuss few also. Then when you solve them, if it's completely implicit, then you do subiterations until the error is reduced. So that's what I was explaining here. Then the pressure velocity coupling, how it is handled, it doesn't matter whether it is a finite difference method or finite method. One can use simple procedure type. And Padankar Spalding group came up with that. And many of the softwares use a simple procedure. And many of the research codes, I would say, fractional step is another method used. And I have given references, Hirt and Cook and all those people. Since Navier-Stokes equations have several phenomena, convection can be considered explicit and diffusion can be considered implicit, or all of them explicit or implicit. So there are so many different ways, different codes can be there, and you need to pay attention. But to control the residue, that means that the error, clearly one should use all the variables, you should solve them by implicit. Any PDE can be approximated. PDE means it can be finite element or finite difference. It can be approximated. Then you can calculate the residue. For one-dimensional problem, I try to show. So for 2D Navier-Stokes equation, one has U velocity, V velocity, and pressure. They are all interconnected. Hence, all the residue must be close to zero for convergence if you really want to have reasonably accurate solution. Then you need to do this. That's what from my book I copied the the iterative procedure, sub-iteration, solve for U, V, and W for every iteration, and then you repeat this until your error convergence is less than the tolerance. If not, many people in many research places, codes, they use momentum, maybe convection explicit, diffusion implicit. So depending upon the nature of the problem in the world, they use them, but finally the error has to be less. So that's where I kind of make a point. Implicit method, you can clearly make sure the errors are less. Then solving, as I said, direct method, iterative methods, many methods are there. Depending upon the problem, people can use point iteration, line iteration, precondition conjugate gradient. It's only for symmetric matrices. Then multigrid method, and I have used multigrid and conjugate gradient combined also, and they are very, very efficient for solving. So you need to be aware of these things, and when you are using commercial codes, you need to know which are the solvers suitable for what, and you need to pick them. And if you are having own your research code, you keep on building them, because in these non-linear problem, computation is very extensive. So the more you can reduce by these proper methods, it will be good. There are also, I just want to mention, in-house research codes one can use, or there are open source programs, OpenFOAM, which is based on control volume method, Proteus, that is a finite element based solver. Then ParaView is a visualization software openly available, anybody can download. And that's where I thought at the end, maybe I will do some workshop on how to use them for a particular data. At least that will give you a chance to open it up. And I said, if there is a place where the organization who was running them, like Professor Sivaraj, I have given them the data so then you can able to download them. And then the ParaView is open source. You can download anytime in your PC. Commercial programs, ANSYS, and there are so many other programs for Navier-Stokes solvers. And TechPlot is one of the visualization software. I kind of mentioned it. Just to give you the major challenge I mentioned, grid generation, I wanted to talk about. This is a particular problem we did in the 90s, and also we continued some in the beginning of 2000. It's a Great Belt East Bridge. I even had an opportunity when I take a cruise in the Baltic Sea areas. This is a bridge connecting Sweden to Denmark. So, so this is a very long bridge. So I was able to, there was a lot of wind tunnel data available. So I use this bridge cross section to model them and validate the computer models. So this is the cross section, all in millimeters, it is shown. So you can see that these are all algebraic grid. I used it at that time. This is how I'm talking about 99 sometime, 2001 or something. So you could see many different forms. My graduate student created it, 3 different grids. On the close-up, you could see that still you cannot see the whole details because the smallest grid spacing close to the body is 1,000th of the bridge width. This is the width, 1,000th of the bridge width. That's the amount of smaller spacing there. Without that, you are not getting reasonable solution. So grid generation, depending upon the problem, one has to design them properly. If not, CFD will not give proper results. And especially this is based on finite element method. I used, here you can see that quadrilateral elements, I used it, and much more zooming, you could see a little bit more. Now you can see the smallest grid spacing, how much it is there. So you could see that. We also used later stages. Because of lack of time, I am not bringing in those things which I am talking about, adaptive finite element methods and other things. We have publications, but I'm not bringing it for discussion in this workshop. Here, what you are looking at, different grids. Even within this, I used, even though I used in the normal direction, I told you that 1,000th of the bridge width. You can see the velocity vector, how small there, which can able to produce the boundary layer reasonably. But still, here in this one, I think if I remember, 170 grid points, how the flow structure is. When I increase to 800 grid points all around, you can see how the flow structure is. So the not only the what do you call it, normal grid spacing, the tangential grid spacing also matters, because the normal can produce the vortex, but to properly transport it, you need to have proper grid spacing and the tangential direction also. So these are all one has to pay. Without that, it will not compare well with experimental results, and then it cannot be a reliable computer modeling. Here you are looking another different views. I try to show that 170 grid points around, 340 grid points here, 640 grid points, 800 grid points. You can see how the vortices on the top and bottom of the bridge deck flow structure varies when you are increasing them. So the more you have proper grid resolution where needed, if it is not there, you are not going to make get good results. That means it will not be a reliable CFD modeling. This one, even though I said I'm not going to go detail into the numerical part of it, I thought at least I'll show this is a model we developed and we validated with the wind tunnel as a moving bridge. You can see the animation of it, how the vortices, when the bridge and the air around interacting, how the vortices are growing, and this is a stage, what we call it flutter stage. So we can able to predict the critical velocity beyond which wind flutter happens. So anyway, I thought I'll put it in. You can see that this is the work done sometime 2005 or before. Okay. Next, I think I will talk some. This is a work we are collaborating, myself and Dr. Sivaraj research group. And the problem is it's trapezoidal geometry with conductive heat transfer problem. So in addition to velocity and pressure, we should also solve for temperature. They are also coupled. In addition to velocity and pressure coupling, you also have the temperature couples with the momentum equation. So it's a little bit more one level complications there. And since it's a wall, it's all no slip wall all around. And the temperature wise, it is shown here, theta equal to 0, theta equal to 1, temperature non-dimensional values, and the normal derivative is 0 here and the same here. And then you can see that it is a sinusoidal variation on this boundary. So we used quadrilateral elements, and using solving for temperature, because the temperature is the one which is driving the velocities, the temperature differences. Then velocity and pressure, every one of them are solved continuously by finite element method. because of the little bit complex geometry. Here for this geometry, if you want, one can use also finite difference or control volume, but implementing boundary conditions and other things are very elegant using finite element. So we chose to use finite element because we also want to do much more complex geometries in the future. So then using this, we ran them, and you can look at the velocity vector diagram that they are produced for a particular problem, and the streamlines I try to show also. So there's a paper prepared by Prof. Sivaraj's graduate student, and I'm assuming she's also in this group. And I think soon the paper will be coming out. And I think the next item which I would like to talk about, because enormous data is produced in the CFD problems, to understand what is going on, you saw that already. I showed bridge visualization where we save the data in time and making animations. So there are so many different ways we have to look at them 2D or 3D data, and then we need to understand what is going on inside, because you are talking about some of the problems I have several millions of points for each time step. When you do it, then enormous data is there. So to process them, we need a proper visualization software. So one of them, this is a very powerful software used in many places, and it's an open source software. ParaView is an open source software, and you can easily download them. If you check the web, you can easily see that. And only the major problem is it can take many different type of data inside, but it has to be given in the proper format. So one of the format I'm planning to show here is in VTK format for triangular elements. I am trying to show the data. This is the data I shared with Professor Sivaraj to distribute to all of you. And even for 2D, the data has to be prepared. In the case of ParaView, it has to be prepared as a 3D data. Even though it is a 2D, you got to do that. That's one thing for ParaView. The provided femet.vtk file can give you more details. And even if you already downloaded the ParaView in your computer, maybe when I'm doing things, if you have the data also, you can also do with me, or any questions as a workshop, you can also ask about it. Opening in ParaView, there are many ways. There are two different ways you could do. You can drag the particular, already the file is written in certain format, like in this case VTK. Then you can drag the file directly in that space where it is drawing. Then automatically it loads it. I will show them when I try to show them using the program. But before that, I thought I'll give you some discussions on that. Then you can or you can also open it and then try to load it. Then you got to choose the proper file format, what is to be used. And I will show you there are so many number of file formats. And every time when I go into that form, I get stumbled actually. So I prefer the first form, much easier. And we will see that. Even this time you will see that when I use the second version, second form of opening, I may stumble. So automatically, then we can see that when I wrote it in the first form, automatically the contour plots are shown. In this case, it's a 2D finite element for stress analysis. It doesn't matter. So it has got data for stresses, or it can be UV, W, anything. You can able to draw them as contours. Then you can also draw velocity vector diagram. So these are the basic nature of it. I thought I will show in this workshop. And we can also look at the grid. So these are the three major ones I plan to show today. And one of my students now, I'm not sure whether he has I requested, I think kind of I mentioned they should also attend, they could attend this meeting because Professor Sivaraj kind enough to allow them. But I don't know whether they are there. But anyway, right now he's working on to get an educational paper on this so that there will be more information. Then it can be available in our GitHub web page and other places also. Okay. One can do contour plots for individual stresses or velocities or anything. In this case, I have 4 different columns of stresses is there, and I will show you with the sample data what it is. And in this case, because this is a program written in a C style, they will have 0, 1, 2, 3 as a numbers in the box under the below magnitude. I will show them. Instead of surface, if one choose surface, surface with edges, then one can also visualize the grid. And I'll also show how to plot the vectors. There is a chapter for CFD especially using open form in my book Selvam 2022. I showed you in the beginning. There is a chapter I have written where how to prepare data for open form, and then how to run them using open form. Then how do you visualize them using ParaView? I have there the open form returns it in a particular format for their own in a binary form, and that also then how to load them. I tried to told you that different formats it can take. So in this workshop, I provided the data FEMET VTK for you to work with me. Hope you downloaded ParaView and your system and you could work with me. So far, here you are looking at one of the magnitude of the stress. You can see that since it is a, you can see the geometry here. It is a symmetry. I took it on both sides, on these sides. So it is the load is applied here. So because of that, this is my first major problem when I'm teaching in my final element class. So I am preparing them in the future instead of TechPlot, which is a commercial program software. I'm kind of preparing these things so that they can use it. So I'm using it also in this workshop. So you can see the grid spacing, how it is, triangular elements, using them. And then when the load is applied, it's a classical solutions are available. So you could see that the maximum stress concentration, they call it, is about 3 times the stress around here. So you would see that the model could be able to produce or capture 2.9. You can see the number 29, whereas the stress is or what do you call it here, it is 10. So you can see the colors. So it is supposedly 3 times the value. So there is a percentage wise, you can see that about 3% or 5% error, but reasonably predicted. So this is a contour plot, and this is a grid. You can able to also draw it. I'm also showing you here vector diagram in a vector form, the displacements. But you can also use it if it's a data with U and V velocity and pressure, then you can also plot the velocities as a vector. So with that, I am also going to I thought that since I didn't know whether you guys have the data, so I put a much simpler data to explain it, how to prepare them for ParaView. So here you are talking about 4 triangular elements and 5 nodes. You can see 1, 2, 3, 4, 5 nodes. For this data, I try to show the VTK file completely. I have listed them because it's a smaller data. So this is the very same one. If you are going to have more number of nodes and elements, then your data will grow big, but the format is the same. So you just need to put the values there. Then you can easily load them. So the other one, FEMET, it has got 69 nodes and 96 elements. So that data is little bigger as an illustration, but that is a benchmark problem I used in my finite element class. So these are the node numbers, X and Y, and this is Z. Because it's a 2D problem, I have 0 here. And you can see that five nodes values are here. Then this is a famous element nodal connectivity data, which is the very basic of the finite element method. So here you are looking at, for each line, you have 3 numbers. That's what this means. And 104, these are the notations, because the node numbers, because it's based on a C program, the node number should start for the element numbers. Nodal numbers should start from 0, 1, 2, 3, whatever. So that's where I can see that 0 to 4, totally 5 nodes, you have that. Cell type, so it's according to, for different unstructured grid, this unstructured grid, there are different types of cells, they call it in ParaView. In this case, the number is 5. So there are 4 elements. So that's what that 4 is, and 5 is put there. Then the scalars, in this case, stresses are scalars. Velocity or displacement is a vector. So I put the vectors here and the scalars here as many rows. Then you can pick each one of them and you can draw contours on that. And this one you can use them to plot the velocity. So I think I have given you reasonably all this information. And I think this is the final thing. I went over different topics, but the main part is I am planning to go in, load the ParaView software and load the data and show them. But in the meanwhile, if it's okay to, can you, Sivaraj, is there any questions here from anyone?
Sir, yes or no, there is no question, sir. By chance, if anyone have any questions, you can ask.
Before I go to open the ParaView.
From the participants, if there is any questions, you can ask.
Okay. Okay, looks
I
like
think it is clear, sir.
Okay. Then what I will do is, I will load the ParaView and see whether I can show them. Well, I'm trying to get out of the full screen mode. It didn't do it. No, it's not doing it. I think page up. How do I get out? Escape is not. Good. Finally, I did it. Okay. Well, I maybe have to get out, I guess, because I'm not able to. Well, let's see whether this way I can see it. Yes, because of all the sharing, all kinds of things on my screen. All right. Let me load ParaView. So if you downloaded the software ParaView, then you will have here is the ParaView symbol. We can upload it. It is reasonably a big software. It is extensively used in all over the world. Since it's an open form, it's a very popular software. So anyway, and I also kept the data right here. So this is the first way I said we can load them. So just drag it and leave it there. Get out of this. So this is a because of too many things in my screen, I'm looking. How do I get this out? I think I can move it. Yeah. All right. Still, I'm not out of the system, I think. I don't know if there's a way I can get out of this. No?
So it has gone.
No, I'm trying to see. I cannot get out. No, I'm trying to see how to make it, because there's a lot of things on the top also. I don't know how to get out of it so I can see the whole screen clearly.
Sir, for us it is very clear, sir. Pair view is very
No, I
clear, sir.
know. For me, you know that when you share
Okay.
the screen, there's a batch of things on the top. You know what I'm talking about?
Okay, sir. Sir, you can click and drag it down, sir. That image.
I can click and drag it down. Let's see.
Yes, sir.
I don't know how to do it. It's just no. I couldn't figure this out.
Yes.
Anyway, all right. Let me try with whatever I have. So I'm going to, okay, let me there. So when I drag them here, so you could see it says on the left, you could see that apply. So simply say, well, there is also some more things are there. I'm sorry. All right, let's see. Because I cannot see things on the top. You guys can see it, but I cannot. I don't know how to get rid of that.
Yes, sir.
All right. So now you can also make a couple of more arrangement, but it's okay. I think it's a 2D, so it's easier, I think. So you just say apply. So it's loading it. So you can see that. Here, this is what the things I have been talking about. So you can see stress, magnitude, it is plotting right now. I hope you all can see better than me because I cannot see well. You say, because of the too many things in my screen right now, because of the communication I'm doing with Zoom. So you could see the values. Then if you want, instead of surface, there are a lot of features, so you have to go and play. I don't do very much because I'm busy with many things, but my students who work on these things, they spend a lot of time. So hopefully many of you who are doing really day in and day out all this work, then the more you spend time, then you would really do well with this. So you can see the grid there. There are a lot of features here. The more you look and see, then you can see interactive select points. So there are so many information is there. So you should spend more time. At least I'm trying to start you guys so you can be able to learn few things and then you can do on your own. All right. So anyway, this is the grid it did. So let me, and also there are a lot of features. Let me see whether I can get out of it. Okay. So here, if you look, see, there are lots of different features here. So you can change the colors, the displays, so many different things. Even there is no distances shown, but you can introduce, see, data access grid. So if you put this, so you can see it put the distances. So there are so many features. This is what I'm saying. It's a very powerful visualization software. So I'm only giving you introductory workshop type, so you can, at least I'm opening you what is ParaView and having a data set to play with, then you can do spend time, then you may do much better than me. So that's one of the features we talked about. You could see that it puts all these I climbed this, and then colors, backgrounds, you can change them. So I'm going to take the grid out right now for the time being. So many features, unless you play with that, you may not be able to see that. Okay, that's one. Then I am going to now wanted to draw the velocity vector. So here is the feature, it says glip. There are, if it's a 3D, then you can do slices, then you can do different directions, all kinds of things. Since I only brought you the 2D data, so it's much simpler as a finite element data. But if it is a structured grid, then you have to, if you can prepare it as a structured grid, then you can do a lot of other things also. So it doesn't matter as a ParaView, whether it is a finite element data or structured grid data, it doesn't matter for it. But anyway, as a workshop is finite element, so I'm introducing as a finite element data here. So for the interactive, I'm going to do say the glip, which means it is going to do vector. For the vector, so I want to choose here itself rather than we have vector. Yeah, displacement is a vector. So I'm going to take velocity. That's what I named it. So I'm going to take it. And now with that, if I go in and clip, if I clip, do that, then also I try to take since it's a 2D data, that particular plane, so I'm going to take 2D glip, you can see, and then if you apply, you will see what happens, okay? So you can see that, you can see the colors it puts it in. Then if you want to change the scale array, so you can move, and then depending upon the nature of it, you can see that. And also I can make some changes. For example, here, the solid color I want at the background, so that I can able to see them. And also here, this eye, you can see, I'm going to take the glip part of it right now. Okay, and then what did I do? I cannot see the screen normally what I see. Okay, so I'm going to do this. Rather than velocity, I'm going to take solid color as a background. So now I'm going to click this glip, so that the velocity vector, I like to see it. So you can see it put a white color. So the background or the colors, you can change them right there, right? Let's see whether we can do some of that also. Solid color. Edit. See, it can. So let's see whether it's a velocity is the color. Let's see whether this is a. Let's see. Yes, you can see that. So you can pick different colors for different one. There are a lot of features here, so one can implement it. Then you are able to see that. Anybody have any questions so far using ParaView?
Yeah, if anyone have any question, you can please unmute and ask.
Or you can text it, and then Professor Sivaraj can read it, then I will respond.
Yes, sure. So I think as of now, no questions, sir.
Okay. I'm trying to see. Still, I have 30 more minutes to talk to you guys. I thought it will be interactive as a workshop, but I didn't see it as an interactive. Last chance. Any comments, questions?
Sir, maybe in the beginning, regarding that mesh generation, we can talk more, sir.
Okay. Let me see. I mean, there are a lot of different grid generation. Maybe I should go to the presentation, you think? All right, let's see. Well, we have done, as I said, even now there is a complex geometry, but very more. It's much more different way I did. This is a presentation I'm planning to make tomorrow, but I can use it also today. So these are all going to be 3D data. I'm having problem of moving.
Yes, sir. Like it will be on some screen.
No, I don't know how to get rid of the top one. You know, when you share, there is a top band is there, like audio, video,
we can click and drag it down, sir.
I cannot able to do it. I'm not able to. Oh, right now, good. At least now. Okay, thanks. So now at least I can able to, because I've been having struggle. All right. So here you are looking at this is there are different ones I am doing. It's a very complex geometry. So you could see this is one of the geometries I'm trying to do it. In this one, it's a 3D. It's about 20 million points or more. So here you are looking at the cross section. This is using actually ParaView. You could see that. And this is a pressure contour of a complex geometry, the flow. And then this is the velocity vector plot. And the flow goes here in this case. Even though it's a closed geometry, we were making inflow and outflow type. So you could see that the flow goes in as like an axisymmetry form 3D and comes down, and then it comes out, and then it is also mixing here. So it's a very complex one. And we are using, in this case, we are using open form and non-orthogonal type, most probably like a brick element type. The grid system is used, and very sophisticated multi-level grids are used. I don't have the plots of the grid, but you have to do a lot of thinking where how much refinement needs to be there, and every different places, what kind of levels of grid should be, spacing should be there. So you have to put it in the open form and then give all these instructions. Then it will create the grid. Even for the grid, I use 8 processes. It takes a couple of hours to develop the grid for this. Totally, I think if I remember, it's about 20 million nodes, just to give you some ideas. So that's one. Feel free to ask me questions. If you have something clearly, then I can ask. Then very similar, there's another geometry. It's a one before the one level before the design. It's also same thing. Then we were developing an axisymmetric software for this, because that way we are less number of grid points, like maybe it is like 20,000 or 40,000 or something. So we can able to manage it. Now you can see the flow geometry. You can see that the flow geometry here, and it's axisymmetric, the same thing what you saw. And then we were able to say this is the flow region. Then here you are looking at the, that means is all these regions, just to see, maybe just to see, but maybe the grid details. Let me see whether I have velocity vector plots. No. The grid resolution, if you wanted to see it, you could see in the velocity vector plots here. See, here you can see the number of points and the resolutions, because when you look at it carefully, we were able to develop the boundary layer very nicely. Look at the refinements and the spacing, so it can able to capture it. So all these features, only if you can make grid, and it is a very complex geometry. You could see the geometry here. So you have to come up with the designing. How can you make required level of grid resolution at different places in this flow geometry right here? These are all the flow region. So one has to decide. Only you can see that with my velocity vector thing, how it was designed. So I worked almost like last about a month to develop this software, so that we can able to have refinements at different regions, the level we want. Feel free, any questions from anyone? This is a geometry. It's one of the largest, what do you call it, tornado simulator, down bust simulator you are thinking of. If you guys are familiar, just to get an idea, this is 200 and you can see that it is in feet. So 280 feet, which is about 70 meters, right? 280, if I divide by 3, how much it becomes? 300 by 3, so 100 meters wide. And then height is 75, 90 foot, let us say, 30-meter height. If you guys are familiar with meters, or if it is in foot, you can see that. So it's a humongous structure. We are helping them in the design. Okay, so you can see that unless you are able to make these proper design, proper grid resolutions, you are not going to capture all the flow features. So grid is a very, very important issue, and you have to come up with sophisticated. In this case, I try to manipulate it in such a way. I am using rectangular grid system, then I come up with a sophisticated way to remove all the curved places and other places where the geometry is not there. So I try to come up with such a class, because to use finite element, I could also use it. The problem here is, for me, I don't know how to control what do you call it, these grid spacings properly in the grid resolutions. How do I do that? I had difficulty. So I come up with my own way of making the grid in certain way. And then I use this kind of, what do you call it? Actually, in this case, it's a staggered grid system. I used it. So depending upon the problem, I pick whatever method, finite element, control volume, whatever I pick. Questions? Oh, here is a question. Can you show the governing equation which you solved? I'm sorry, let me see the text properly.
Professor, the question is, can you...
Let me look. There are some questions here. See that. Okay. Jacques. Okay, please. How to introduce equations and boundary conditions on ParaView? Okay, in the ParaView, you are not introducing equations or boundary conditions. Your CFD software program, anything, you either your own program or some other commercial program, from there you get the data. That data, when you are using, that's a finite element, let's say finite element or control volume programs, yes, commercial program, ANSYS, or your own research code, any of them. First, you get the data. Like the data I shared with Professor Sivaraj for you guys, or the one I showed for a simple one. I already solved it through a finite element program, and I got the data. Then, so that means is it doesn't have equations and boundaries. Already, it's all there in the data. Then you use the visualization software to visualize it. I hope I answered it. If not, feel free to ask some more questions. Then let me address the other one in the meanwhile. How to show heat distribution on ParaView? Like I showed you, what do you call, in this case, I showed contour plots for, what do you call it, as a contour. And then I also showed, the next one I showed you, you saw the pressure contours. Did you? I hope you remember. Just a minute. Let me see whether how I can able to. Still, I'm sharing, right? Yes. Let me see how I can go to this. Yes. So if you look at this, you can see that. But this one I use tech plot. It doesn't matter, depending upon how you write the data to which software and you use it. So you can see that this is a pressure. This is a pressure contour. So as long as you have them in the scalar data set in my presentation today, you saw that. Let me see whether I can. I already killed it, I think. Sorry. So these are the coordinates. These are the element nodal connectivity. So you can see that scalar. So you can have scalar pressure, all the nodes you can have. Right now, I have stresses. That doesn't matter. So you can put pressure there, then you can plot it. I hope I answered that text part of it. Where is the text now?
Professor, I can read for you. Sir, how to show heat distribution on ParaView?
Yeah, same thing. That's what the temperature as a scalar, then you can show them.
Yes, Professor. And sir, can you repeat simulation
I think
in
I showed
ParaView?
him also here, right? Did I not show the contours here? Let's see. No, yeah, right. The temperature, is it that? No, that's a Streamlines. Okay, I did not show the velocity. Well, I was thinking that whether I can go in and show them, or you put it in the scalar, anything you put it in, you can plot them as a contour. Okay. Alright, let's see what other. Did I answer all of them? Heat distribution. Can you repeat simulation in ParaView? This is Bhuvana. What do you mean by repeat simulation? I told you that ParaView or TechPlot can only view the data you developed from your CFD program. So anything you need to do simulation, it should be done in your finite element program or finite difference program, the CFD program. Then you take the data and then you visualize it. You can make, I told you that I have shown you contours, vectors. I also showed you animations. If you can make in time these data, then you can make animation. Let me see, there is some more there. Professor, please, can you show the governing equation which you solved and got these results? I think these are all incompressible flow. So the equation, I put it in. Only thing is the last one I showed, because it's a high Reynolds number flow, I also used large eddy simulation, turbulence and other things. But if you can read my book and other places, you can get to know more. But the governing equations are same, incompressible flow. Only thing is you have some modification to include the turbulence effect. Vijay Kumar means ParaView is a visualize the output data. Yes, it is. You need to develop the output, then you can use them. Okay, there is one I thought, did I, Basha asked something, I thought, did I miss? Sivaraj, I thought there was one text I saw from Basha.
Sir, I'm checking that.
I thought I saw, but now I don't see it. So,
Yes, sir. That is another Basa, sir.
ah,
Like the question is, Professor, please can you show the governing equation? That is same question you have
I see.
already.
I already addressed it.
Yes,
Okay.
Professor. And
Okay.
then one person wants, sir, can you repeat simulation in ParaView? And one person confirming that means ParaView is a tool to visualize the output data. That is S.
Okay.
Yes, Professor.
Any other question?
Yes, Professor. I think the participants may not have much questions because the explanations was very clear.
Okay. Well, I still have anyway, according to our time wise, another less than 15 minutes, right?
Yes, bro. It is not a problem, Professor.
Okay.
Yeah. So if there is any questions from the participants, you can ask. Yeah. So in the absence of the questions, may I ask the organizers to display the certificate?
Oh, I stopped sharing, right?
Yes, sir. Yes, sir.
I thought I stopped sharing. Did I not stop sharing?
Yeah. May I ask the organizers to please
Still,
get
I'm
of
not.
Professor Panneer Selvam?
Yeah.
Yes. So, sir, really, we are very happy that we can able to see the lecture and understand many things, starting from the explanation about the types of grids, like staggered grid, non-staggered grid, etc. That is very precise. The explanation pertaining to computation complexities are very informative. The information on the difficulties with the different solvers and which solvers should be used at particular time. That is very interesting. How the contour of vortex strength varies depends on the grids is well explained, and the importance of grids is well understood. So your insight on the heat transfer aspects and fluid flow of the trapezoid in the trapezoidal cavity, it is very useful. the detailed explanation of the finite element method data for 5 nodes, 4 element, that is very informative. So the graphs and other things you have shown visualized through ParaView is very useful. So on behalf of the organizing committee, we thank you for giving your lecture on the topic FEM to study fluid flow and heat transfer in a trapezoidal cavity. So we thank you very much, and as a token of appreciation, we would like to present this certificate to you. And
Thank you.
thank you, sir.
See you guys then, because it is like close to midnight for me.
Yes, sir.
So see you guys.
Thank you, sir.
Bye.
Bye, sir.